Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to introduce Magda Balazinska from MIT. She's currently finishing her PhD thesis with Hari Balakrishna at MIT. And what she's going to talk about today is about load management and fault tolerance in distributed stream processing system. Magda?
Okay, thank you. Well, thanks everyone for coming. So what I'm going to present today is work that I have done as part of my thesis and also as part of the Borealis project. So let me first start by saying a little bit more about the kind of stream processing that I have in mind. So as an example application, let's say that we would like to monitor a large network. So we're going to deploy network monitors and put them in the various subnetworks. And each one of those monitors is going to produce a continuous stream of information. For example, information about the connections that were established within each subnetwork. So what we would like to do is take all these streams and continuously process them, aggregate them, correlate them, filter them to produce various outputs of interest. For example, alerts if there's an intrusion going on in the system, or alerts if there's some kind of anomaly that is being detected. So this is an example of a stream processing application because the user is simply waiting for results to arrive. The data sources are actively pushing streams into the system, and the system is continuously processing the data to produce results with low latency. So these types of applications occur in various domains. So I already mentioned network monitoring, but there's also financial services, where, for example, applications are going to continuously process market feed information, or sensor-based environment monitoring, where we would like to place sensors inside a building or outdoors. Each sensor is going to produce a stream of measurements such as temperature readings, pressure readings, and we would like to process these streams to monitor the environment continuously. We can put sensors on patients for medical applications and observe the well-being of the patients. We can put RFIDs on the equipment, RFID tags on different pieces of equipment, and track the equipment as it moves through different locations, for example, within a hospital. So there are many applications that perform these kinds of stream processing. And of course, we could develop a system that will support every single one of those applications individually. But what we would like to do is have one system that can support all these applications simultaneously, something like a database system. But the problem with databases is that they are designed to operate on static data, stored data, not this data that is continuously streaming. So therefore, various groups have developed what are called stream processing engines. And these engines are geared towards these stream processing applications, and they provide data management capabilities for streams. So I have mentioned a few of the project names that are the projects developed by the various groups. In this talk, I'm going to focus on Borealis. Borealis is a stream processing engine that we have developed at MIT in collaboration with Brown University and Brandeis University. And Borealis is actually one of the first distributed stream processing engines. It is now publicly available, and a few groups have actually already downloaded it and are playing around with it. So in Borealis, the application logic takes the form of a data flow. So on one end, we have input streams. These are the streams that are going to be produced by the data sources. Each one of the stream is simply a sequence of data items, or what we call tuples. And as these tuples, as these data items are going to arrive, the various operators are going to process these inputs continuously by performing computations over windows of data. So every operator is going to buffer some of those input streams and accumulate them and operate over those windows of data that are going to move with time. So basically, with this data flow, we're going to transform the input streams into other output streams that we can then send to the client applications. And just to be more specific, yes?
Is the window size synonymous with the buffer size?
So the window size is basically how much buffer, how much data the operator is going to buffer. So for example, for a window join, then if the window size is 60 seconds, we're only going to join tuples that are going to fall within this 60-second bound. Okay, so and each one of the tuples is simply a data item that has a set of attribute values. So you can view this as a row from a database table. So for example, the tuple might contain a temperature reading value and also the time when the reading was taken. So of course, we could take all those operators that form all this application logic and run them at a single location. But because for many applications, the data sources themselves are going to be distributed, and also, to improve the performance and scalability of the system, in Borealis, we distribute the application logic across multiple processing nodes. So let me show you a concrete example of a query. So this is a network monitoring query. What you would like to do in this query is take the input from the network monitors, and in our case, this input are the connection summary information. And what you would like to do is create an alert if a source IP is detected to initiate more than 100 connections within a 60-second window, or is trying to connect over more than 10 different ports, or does both at the same time. So to count the number of connections, what we would like to do, and this is what you can see in the blue box up there, is we would like to take all the input streams from the network monitors, union these streams into one stream, and then take the data for that stream and perform a windowed aggregate. The windowed aggregate is going to partition the data per source IP, so do a group by source IP, and then count the number of connections for each source IP and for each window of 60 seconds. We can then take the output results that are going to be streaming and filter them using the desired threshold that we are interested in. And we can do something similar to count the number of distinct ports that an application is trying to connect over. What is interesting is that if you would like to find an application that belongs, if you would like to identify a source IP that belongs in both categories, we can then join the two output streams, once again by performing a windowed join. So we're going to join tuples that have the same source IP, but only if they fall within the same windowed interval. So this is an example of an application, and it is distributed across 3 nodes in this example. So there are many challenges that we need to address if we want to build these types of distributed stream processing engines. And in this talk, I'm going to address 2 of them. First, as a distributed system runs, nodes will fail or the network will fail. So how do we protect the system against these types of failures? And second, as the input load varies, the load imposed on the system is going to vary. So how should we handle these load variations? So let me start with fault tolerance, where I'm going to first define the problem and indicate our contributions and challenges. And I will then describe our fault tolerance protocol and show you some experimental results. So first, what kind of failures can occur in a distributed stream processing system? Well, one type of failure is that any one of the processing nodes can simply crash and stop. And if this occurs, we're going to lose all the state that we have accumulated at the node. And this is also going to disrupt processing because the downstream node or downstream nodes are not going to receive results anymore. But even if a node does not fail, the network could fail. And if the network fails, which is highly likely, especially if we distribute the processing across the wide area, then any subset of nodes might be unable to communicate with one another. And once again, the processing will be disrupted. So these are the 2 types of failures that we would like to protect the system from. And so we will not be looking, for example, at the failures of the data sources themselves. But what do I mean by protecting the system against failures? Well, what we would like to do is really mask failures and basically provide 2 properties. One is availability. Even though nodes will fail or the network will fail, we would like to ensure that the clients that are just sitting there waiting for the results get these results quickly. So we want to guarantee this low per tuple processing latency in spite of failures. But second, we also want to ensure consistency, which means that even though failures occur, the tuples that we're going to stream and send to the applications are going to be the same as those that we would have sent if the failure did not occur. So what we can do, of course, is take each one of the processing nodes and replicate it. And by doing that, even though some nodes will fail or will be unable to communicate with one another, we can mask many failures. Yes?
I'm not sure that your data flow graph is deterministic to begin with.
So I'm going to get to that in a few slides.
Okay.
But even if it is, and again, the picture you have right here, you've got the network to one of the sensors. There's no way you could possibly be consistent because the data can't even get out from it.
Oh, correct. So this is exactly what I mean to say, is that for some types of failures, a node might be unable to communicate with any one of the replicas that is producing one of their input streams. And in this case, we will be, in fact, as you're pointing out, unable to provide both availability and consistency. We basically have to choose.
Right.
So either we're going to say if the node is unable to get one of its input streams, either the node has to block. And in this case, we guarantee consistency, but we are going to sacrifice availability because we are not producing any results. Or what you're going to do is say, well, let's allow the node to continue. But in this case, we do provide availability because we are going to produce results. But the results that you're producing are no longer identical to those that would have been produced without the failure.
Yep.
So what should we do? So if we go back to our sample applications, for example, in a network monitoring application, if at some point we lose connectivity with half of the network monitors, then processing the data from the remaining network monitors might suffice to detect some intrusions or to detect some anomalies. So in this type of applications, it is important for the client that we continue processing even though we do not have access to some of the inputs. However, once the failure heals, we would like to go back and let the client know exactly what happened in the network. Did we miss some intrusions that have occurred? Did we miss some anomalies that have occurred? So as another example, if in a military application, we might use airplanes or other sensors to detect the position of various enemy units. If failures occur, it is still useful for that application to know about the location of any of the subset, any of the enemy units at any time. But when the failure heals, we would like to go back and inform the clients exactly of the location and the movements of the different enemy positions. So as you can see in these types of applications, when failures occur, we want to continue processing because the data is often useful. But when the failure heals, we would like to go back and correct the data that we have produced such that the application can get the complete correct output stream. So we can map these requirements onto the following 3 fault tolerance goals. Our first goal will be, no matter what happens, we would like to ensure availability. We want to continue to produce results. What is interesting is that many applications can tolerate some increase in processing latency. So for example, if I'm monitoring a network and I'm usually getting results within 20-30 seconds, it might be totally reasonable to wait and get results in 45 seconds when a failure occurs. But we want to favor availability. And the second goal will be to ensure eventual consistency. When the failure heals, we're going to go back and correct the results that we have produced such that the clients can see the complete correct stream. And actually, we're going to take this goal and push it further. Because every time we're going to produce a tuple that results from processing a subset of the inputs, when the failure heals, we will have to go back and correct that tuple. So these tuples will cause overhead in our system. So what we would like to do is avoid producing these tuples, or if possible, choose techniques that produce fewer of these tuples during runtime. So we're going to try to minimize inconsistency that we define as the number of tentative tuples that the number of those possibly incorrect tuples that we produced. So our overall goal is going to be to minimize the inconsistency in the system, subject to ensuring that the maximum delay for each processing node is going to be below this user-defined or application-defined threshold D, which is our measure of what kind of increase in the processing latency any application can sustain. So given these goals, our contribution is the following. We're going to propose a protocol that enables us to achieve the 3 goals that I have mentioned. Second, we're going to enable applications to define this flexible threshold between availability and consistency by indicating this maximum threshold D. And finally, we have to modify the data model for stream processing. The model that I have described earlier is that of an append-only stream. tuples arrive on a stream, and operators perform computations over windows of tuples. Whereas here, we would like to, once a failure heals, go back and correct the data that we have produced. So we need a different model that will enable us to have these types of corrections. So the data model that we propose is the following. A tuple will no longer have only a set of attribute values, but a tuple will also have a type. And that type will indicate if a tuple is either stable, which means this is a correct tuple, it's consistent, and it is immutable. This is the final result. Or a tuple is tentative, meaning that a failure is occurring and we are processing a subset of the inputs, and those are the temporary results that we're going to produce. So a tentative tuple is not just any kind of erroneous tuple. A tentative tuple is one that results from processing a subset of the inputs. And furthermore, we guarantee that once the failure heals, we're going to go back and correct these tentative tuples and replace them with their stable counterparts. So of course, we could correct tentative tuples one at a time. But because when a failure occurs, so a node goes down or nodes get disconnected, we are typically going to produce bursts of tentative tuples. We're going to correct them by producing an undo tuple that will indicate what suffix of output tuples we are correcting, and then we will replace them by the stable version of these tuples. So given this data model, before showing you the details of our protocol, let me show you a concrete example. So I'm going to run two Borealis nodes, a node and its replica. Both nodes are going to process 3 input streams. My availability requirement will be to always produce results within a 3-second processing delay. But we are going to cause a 20-second failure on one of the input streams. So what we should see is first stable tuples before the failure occurs. As the failure occurs, to guarantee our first goal, which is availability, we're going to produce tentative output tuples, and some tuples might even be missing. And when the failure heals, we would like to go back and correct these tuples. So let me show you this right here. So actually, Borealis is written in C++, but the GUIs that you're going to see are actually Java GUIs. So I am now starting Borealis and one of its replica. This is the input application that is going to produce the 3 input streams. And this is the output application that is going to monitor the consistency and the availability of the output. So in the bottom window, we have the availability, which is the maximum processing latency, and we want this to be below the 3-second bound. In the top window, you have the consistency. We have 1 square per output tuple, and green means that the output tuple is currently correct and consistent. And these are the 3 input streams. So now, when a failure will occur, so now the failure occurs. So we can delay the input tuples somewhat, but eventually we have to start producing tentative tuples to make sure that we meet our availability requirement and produce tuples within this 3-second bound. And we're going to do this until the failure heals. Now watch what happens when the failure heals. So when the failure heals, as you can see here, so let me pause the output now. Once the failure healed, what happened is that we went back, produced this blue tuple here, which is an undo tuple, and corrected all the tentative tuples that we have produced earlier. So all these tuples should be green. I'm coloring them darker green so you can see which tuples have been replaced. And we were doing this until we corrected all the tuples and produced another tuple to indicate that this is the end of reconciliation. But what is interesting is that no matter how long it takes us to perform these corrections, we always make sure to continue to process the most recent input tuples such that we maintain the availability requirement of producing output tuples within this 3-second window. So this is basically our goal, and this is an example of how our protocol works.
I don't understand how your nodes can tell the difference between a network failure or a sensor failure or something that stops tuples from coming and the source just not generating them.
So let me get this in 2 slides.
Okay.
So if I don't answer this question, just...
Oh, I'll remember.
Yes. Same as the determinism question. So first, what are some of the challenges that we have to address to provide these properties? Well, the first challenge is that if we simply take a node and replicate it multiple times, On one stream, the tuples will be in order. But if we have an operator, such as a union, that processes multiple input streams, then the inter-arrival times of the tuples will change the state of the operator and will change the output that the operator produces. So if we simply replicate the processing nodes and let them run, their state is going to be different because it's going to depend on the arrival times of the different tuples. So the replicas are going to diverge. And because we have dependencies between upstream downstream nodes, once these replicas will diverge, they will produce different tuples. These tuples will feed into other downstream nodes, and these downstream nodes will diverge in turn. So we will end up having all the replicas in a different state, and it will be extremely difficult to provide any kind of fault tolerance. So we need a way to keep the state of the replicas consistent with one another. But the state is not a persistent state. The state is this large, transient, rapidly changing state. So if we want to reconcile the state, we basically have to go back and reprocess all the tuples in the final correct order. So reconciliation in our context is going to be very expensive and very disruptive. But we still have to perform it, and we have to do it in a way that always maintains availability, because this is our number one requirement. And of course, we want to handle various types of failure scenarios. So given these challenges, we also make a few assumptions. First, we assume that we have enough capacity in the system to replicate each one of the processing nodes such that all the replicas are going to process data, and the downstream nodes can get their inputs from any one of the upstream replicas. We also assume that operators are deterministic. So this goes back to your question, such that an operator is the state of the operator and the output is only going to depend on the values of the input tuples and the order in which they are processed. And actually, this is the case. Most stream processing operators are indeed deterministic.
But your queue has like this 60 seconds delay or limit.
Correct.
Okay, you cannot preserve deterministic. Let's say you have like some more delays in one case than the other in the network, and the first 60 seconds expired and have to process something.
Yes.
The other one just have one token left in the network.
Correct. So basically, we are going to buffer the input tuples as they arrive. When an operator gets some input tuples, the window that defines the computation, the size of this window does not depend on any kind of actual wall clock time. The window is defined on the values of the attributes inside the tuples themselves.
Exactly. That's why the 60 seconds is a limit.
So,
Right.
so I can buffer more tuples than the 60 seconds.
Right.
So I'm going
That's
to
a
buffer.
parameter you're setting, but maybe we can take this offline. That's a parameter you're setting.
Correct.
That you have to do something when the time expires.
So there is no time expiring. So basically, when the tuples arrive, if I have a tuple with a value 100 for the time value that I'm using to define the window, I will keep this tuple and accumulate until I see a tuple with value, for example, 161, if my window is of size 60. And then I will compute the value on this window. So the window itself is really depending on the attributes inside the tuples, and that's how the window moves. And that's why we're getting determinism. If we had these timeouts, then we would get non-deterministic.
But then your buffer size is unlimited.
Yes, so the buffer size, we can view it as unlimited, but basically the operators are going to assume that the tuples are arriving in order, and they can move these tuples like that.
Right.
So we can maybe talk even more in detail. Yes?
The standard thing that you do when constructing these networks is that you have a sort of a null data source that's really just the wall clock, and you feed that into the left end of your graph so that nodes that want to do something that is time dependent have a deterministic source of time.
So basically, currently we disallow anything that would be completely time dependent, and in our case it would be only timeouts. All the computation is determined on the values inside the tuples themselves.
Right, but if you define a data source to just be a clock that says, and now the time is, and now the time is.
We could add that.
Then at that point, a timeout is now a deterministic operation downstream.
Correct. So we could add this, definitely.
That's not something you normally do.
We just don't do this. But actually it's neat, so we should maybe add this to the system. Correct. Okay, so we also assume that nodes buffer the output they produce. And in this talk, I'm going to assume that nodes buffer all the output they produce during a failure and recovery. And finally, we assume that nodes communicate over TCP such that tuples do not get reordered on a single stream.
Can I ask one more quick question
Yes,
before
yes.
we leave this topic? There was still what seemed like a non-deterministic timeout in that. So in the example that you showed of the software, there was this constraint that it had to generate output within 3 seconds. And so that doesn't seem to be 3 seconds according to tuple timestamp. That was 3 seconds of lost
Correct,
time.
correct.
So there might be differences in when that 3 seconds expires. It seems that the operator is forced to emit output based on whatever happens to be in its window at that time.
Exactly. So what happens is that in this case, so this maximum processing delay is normally much greater than the windows over which we operate.
Okay.
So we only need to use that delay and expire with this timeout when failures occur, or there are really great delays that we will then consider as failures. And when this happens, we're going to start producing these tentative tuples, meaning that, well, maybe what I'm producing is no longer consistent. This is just the tentative data, and when the failure heals, we're going to go back and reprocess the input and correct it.
So what it sounds like you're saying is that a failure of a data source itself is a deterministic form of data. That the data generated, even in case of failure, is deterministic. It'll arrive. That is, all replicas of the operator will see the same data, even if that is failed, even if it represents a failure.
Yes, so currently we do not look really at the failures of the data sources. We assume that the data sources are going to produce tuples, go through maybe some proxy, because some data sources might not be able to handle, sending data to different replicas, and that this proxy, either it produces the data and sends it to all replicas. So of course it has to log the data before sending it, such that if it crashes and restarts, then it will be able to continue and send the same input to the same operators. And if the data sources crashes, for us this means that the data sources is not producing any data into the system. So let me go into the protocol, and then we can discuss.
Just one more to make sure I understand this right. So the way this works, the tentative tuples are non-deterministic.
Correct. The tentative tuples can be different at the different nodes.
But you back them out later.
Correct.
Right. Okay.
Yeah. So given these challenges and given these assumptions, our fault tolerance protocol works in 3 phases. The basic idea is that each node, each replica, is going to monitor its own consistency and its own availability, such that under normal operation, we define a new operator that will make sure that all the replicas remain consistent with one another without having to talk to each other. When a failure occurs, a node is going to make sure that it processes whatever data is available within this maximum bound D. But at the same time, the node will try to avoid inconsistency, or if it cannot avoid inconsistency, choose techniques in which it can meet the availability requirement by producing fewer tentative tuples. And when the failure heals, to ensure eventual consistency, we're going to go back and require that each node reconciles its state and also corrects its output, such that the downstream node will be able to reconcile its state in turn. And at the same time, because we have to maintain availability, we're going to continue to process the most recent input tuples, such that the downstream nodes have access to this information. So we implement this protocol by having each one of the replicas, each node, implement the following 3-state state machine. So in stable state, we only maintain consistency and detect failures. When a failure occurs on an input stream, a node goes into upstream failure state. When the failure heals, the node will go into the stabilization state, where it's going to reconcile its state and correct its output. So let me now talk to each one of those states in turn. Starting with the stable state, where we want to maintain consistency and also detect failures. So to maintain consistency, because we have deterministic operators, we have to make sure that all the replicas process input tuples in the same order. And we would like to do this in a way that the replicas don't have to talk to each other to agree on what this order should be. Instead, we introduce an operator that we call S-union. And this operator is going to take multiple input streams and sort the tuples on these streams in a deterministic fashion. The challenge is that the rates of the input tuples on the different streams may be very different, and the tuples are not necessarily sorted on any one of their attributes. So what we propose is that data sources periodically produce boundary tuples, which are kind of like keep alive messages. And the S-union operators will use the values in these boundary tuples to define buckets and place tuples in these buckets, and then apply a deterministic sort function in each one of those buckets of data. And what is interesting here is that by doing that, we will ensure that the order is the same at all the replicas. But also, if an S-union operator receives tentative inputs or does not receive boundary tuples on one of the inputs, then we know that something is wrong. We know a failure is occurring, and the node transitions into the upstream failure state. Yes?
So I see how that gives me order on each of those channels, but the important feature here is that I have to order the two channels as I'm merging them, right?
Correct. So we're going to get basically, on one stream, the order is always preserved because we communicate over TCP, so we don't reorder tuples. If we have multiple input streams, then those input streams are going to have boundary tuples. So we can then use the values in these boundaries to define buckets and basically merge both streams into one bucket and apply a sort on this bucket.
So the boundaries are the same time granularity?
So they usually are the same time granularity, but basically we're going to use the values. So you can say that we're going to buffer.
No, I mean, like, the point is that all the streams are using the same size buckets so that when you put them into the same buckets, you...
Yes, so the S-union is going to define the bucket, and the boundary tuple guarantees that all the tuples that follow will have whatever value we use for the sorting will be greater than the value within the boundary tuple. Therefore, we know that we can basically sort all the preceding tuples deterministically and do this across the streams.
Do you assume a synchronized time? Or?
You do not need to have a synchronized time. So, of course, ideally, if you use, for example, NTP on the different data sources, and they use the real clock to define these boundary tuples, then the tuples will be processed roughly in the same order in which they are produced. But we can use any other attribute value for this tuple. And if those values are not quite synchronized, then it will determine simply the order in which the tuples are processed. But it will still give us a deterministic order. So now let's assume if we are missing these boundary tuples or receiving these tentative tuples, the node transitions into upstream failure state. And in this state, our number one goal is to ensure availability. But at the same time, we would like to avoid introducing inconsistency in the system, or at least minimize this inconsistency. Hence, when a node fails, the first line of defense will be for the downstream nodes to find an alternate stable replica and get their inputs from that replica. And since all the replicas are consistent, we can have this switch be seamless. As a second line of defense, if a node cannot hear from any one of its input streams, then we have this bound, this maximum processing latency that we can use to suspend processing and hope that the failure is a short transient failure, and we can mask it by delaying without introducing inconsistency. But if the failure is too long, then the node has to proceed and process the remaining input streams that it can process to make sure that we meet our availability requirement. And when this occurs, the node is going to start producing tentative tuples, and these tentative tuples are going to propagate through the network. And this will continue until the failure heals. To determine that a failure heals, so each node is going to determine that the failure healed for itself, either because, like the first node there, it's going to be able to communicate with another upstream replica that will be able to produce the missing tuples, or because the node will receive the corrections to the previously tentative tuples. So when this occurs, the node transitions into the stabilization state. And in this state, we have to go back and reconcile the state of a node and correct the output it has produced, such that the downstream nodes will be able to reconcile in turn, and eventually the clients will see the correct output. So let me now tell you how we are reconciling the state of the nodes. So there are different techniques that we can use. And one of the techniques that we have examined was to restart simply from a checkpoint. So at runtime, a node is going to periodically checkpoint its state. Once a failure occurs, we're not checkpointing. When the failure heals, we can go back and restart the node from the checkpoint. So if we do this, so we restart from a checkpoint, reprocess the input data, we are going to reconcile the state of the node. However, we are not going to correctly, to properly correct the output tuples, because we're going to produce some duplicate stable tuples, and we will never produce the correct undo. So to properly correct the output streams, we introduce another operator, which we call soutput, this operator is going to monitor an output stream. And at runtime, it will simply forward all the tuples that it sees, and it will remember the last stable tuple that it has seen, such that if we restart from a checkpoint, as output will be able to eliminate the duplicates and produce the correct undo tuple. And of course, this is a little bit more tricky if failures can occur during recovery, as output has always to guarantee this semantic, even though we might checkpoint or restart while we are recovering. And actually, in terms of multiple failures, because our goal is to produce as few tentative tuples as we can, when a failure occurs and affects multiple input streams, in our scheme, we're going to wait for all the input streams to be corrected before we reconcile the state of a node, such that we can correct tentative tuples with stable tuples rather than correcting tentative tuples with other tentative tuples. And actually, even though a failure can occur while we are reconciling, the node will always delay introducing new tentative tuples into the system and will checkpoint its state before doing that, such that when we will reconcile from the second failure, we will not have to go back and reprocess all the tuples from the first failure as well. So with this technique, in terms of performance, we have to pay the cost of these periodic checkpoints. But what is interesting is that because when a failure occurs, the first thing that we're going to do is suspend processing. Then we always have time to checkpoint the state of the node when we go into upstream failure. So we can avoid these periodic checkpoints and only checkpoint when the failure occurs. But of course, the reconciliation time is still going to increase linearly with the failure duration and the state size, because we have to reprocess all the input tuples.
So if you go into checkpoint right then, you pick sort of the most time-critical time in your system in order when to force your checkpoint, because you're gonna sit around and wait for input data to arrive until you're close to your bound.
Correct.
Because you prefer that it would arrive and you don't have to do this at all.
Correct.
And then when you decide that things are bad, then you checkpoint.
So actually,
so it's going to put you really close to missing your bound.
So actually, in our case, we're going to start checkpointing much faster. Basically, you want to checkpoint even though we might be checkpointing for nothing.
Okay, so
optimistically.
So it's checkpoint. As soon as something's a little bit late, it'll just take a checkpoint.
Correct. Yes. But basically, you can avoid this regular checkpoints. You can only do this when something is at least going a little bit badly. So, yes.
Do you assume another mode of failure, or like denial of service kind of failure, that got a lot of packets all of a sudden from one particular channel? Okay.
So,
do you consider that a kind of failure or not, or just regular?
So I'm not sure I understand the type of failure you're mentioning. So we do assume that the network can fail, for example, and nodes will be simply unable to talk to each other.
Right.
Or that the node will fail and it will stop producing any data.
So your failure is always something stop. You always can detect that from waiting on like an input stream.
Exactly. So basically, because the node does not receive any data or does not receive boundary tuples or is receiving these tentative tuples, then the node knows that something is wrong with the upstream replica. And actually, each node is going to monitor all the different replicas. So it knows the state of all these replicas. So if one of them is in upstream failure and the other one is stable, the node will be able to reconnect to the stable replica and continue getting data from there.
I guess what I'm saying is you can have a node that's failing, which basically produce a lot of messages than it need to, or than it used to be in the.
Oh, okay. So you mean, for example, Byzantine failures, where when the node fails, it starts producing just random results that are incorrect.
And a lot more often than.
Correct. So I do not address these types of failures. I only look for node failures that fail stop failures. Okay. But that's an interesting kind of future work. How could we add this type of failure as well? So there are other types of reconciliation. And for example, one approach would be to undo and redo all processing. So I have also examined these types of techniques, but with undo and redo, we ended up having to do a lot more modifications to the operator. The approach was much more complex, and yet did not offer us better performance. It was still giving us slower recovery and a higher overhead. But even if you go with checkpoint redo, the problem is now we are reconciling the state by taking the node, going back in time, and reprocessing the tuples. So we are correcting the state. But how can we maintain availability? Because now the new input tuples are going to continue to arrive, and we are unable to process them. So what we propose, because availability is our first goal, is to use two versions of the query network. One version that is going to go back in time and reconcile, and the other is going to stay in upstream failure state and continue to produce the most recent results. But instead of having a node spawn the different versions locally, because we already use replication, we basically require that a node be able to communicate with another replica and request that the other replica postpones its own reconciliation before it can basically become unavailable because it's going back and correcting the previous results, such that the downstream nodes will now be able to communicate with both replicas and receive the corrections with possibly delay, and at the same time will be able to receive the stream of the most recent data from the replica that remains in upstream failure state. And the downstream nodes can now process both streams until they receive the reconciliation done tuple, which indicates that now the most recent stable tuples are being produced without delay. And at that point, the downstream nodes no longer need to process this second input stream. Yes?
So does this mean that you have to have multiple replicas for every portion of your stream processing system?
Yes, correct. We do replicate every portion of the stream processing engine, such that because the node could fail, and if the node doesn't fail, but for example starts reconciling, that it is not processing the most recent data. So of course we could also run the two versions locally on the same machine, but because we already replicate across machines, we decide to use these replicas. Yes?
So I had assumed that this was an orthogonal replica. You had replicas across hosts for reliability, and then you had replicas within a host. You'd have one replica running the availability computation, one of them running the consistency computation. So, but then it sounded like your answer to Alex's question was that you, in fact, you take your replicas that are set up for the first two that you set up for reliability on separate hosts, and you just assign one of them to be the availability replica that's remaining in failure mode, and the other one is the.
So we don't assign this statically, but basically at runtime, we want to avoid. So we could, for example, run the two versions locally. So have every physical node run the two virtual nodes, one that remains in upstream failure and one that reconciles. But because we already replicated, what we want to avoid is having both replicas reconcile at the same time, because then the downstream nodes do not have access to the results.
Okay,
so all we want to do is at runtime.
So you're sort of reusing the replication for two purposes, one for reliability and at the same time also for the efficiency of doing both of these computations at the same time.
Yes, correct. But we could also run them both on the same node.
So certain kinds of operators have the property that when you turn the data back on, they'll stabilize without needing to look at the old state. So for instance, the example that you had at the beginning, where the operator was saying, have you had 100 connections in the last minute?
Correct.
Once it's seen, and if you get a dropout from minute 2 to 5, then it's going to produce tentative tuples that say, I have no idea.
Yes.
And then it comes back on at minute 5. After minute 6, you can actually produce stable results for that particular operator because it doesn't.
Yes, correct.
Do you deal with that, or was it not worth special casing, that kind of thing?
So basically we do not, so what will happen in this case is that we are going to treat this still as tentative until we reconcile the state, because we do not, all the operators will remain in failure mode until we reconcile. So the short answer is we do not treat this as a special case. We will continue to produce them as tentative, but the tentative and the stables will be identical.
Right.
But we could optimize it. Basically.
I have no sense as to whether that matters. So.
Yes, that's a good point. So basically, overall, our protocol provides the following features. In stable state, we have this S-union operator that maintains the consistency of the replicas. In upstream failure, so when a failure occurs, we ensure availability while trying to avoid inconsistency. And during stabilization, we're going to go back and reconcile the state to ensure eventual consistency and avoid having all the replicas reconcile at the same time to maintain availability. But there are two questions that we would like to still answer. First, does this work if we have a network with multiple nodes in sequence? Can we still provide the proper availability requirement? And second, because we have this maximum delay bound, how much could we gain in consistency by always trying, once a failure occurs, by always trying to run on the verge of breaking our availability requirement? How much could we save in terms of tentative tuples compared with processing these tuples as they arrive? So to answer the two questions, I would like to show some experimental results where we're going to run two replicas of a node and process data through 1 up to 4 nodes in sequence. So we're going to start by running 1 node and its replica, then 2 nodes and its replica, 3 nodes and its replica, 4 nodes, and also the replicas. We're going to cause a failure on the input stream and then look at the availability and at the consistency on the output stream. So here are the results for the availability. On the x-axis, we have the depth of the chain from 1 to 4 nodes. On the y-axis, we have the maximum processing latency, which is our measure of availability. So in this graph, we want the processing latency to be low to have a good availability. So the lower results are the good results. And in this experiment, once again, we have used this 3-second bound. So our guarantee is to ensure that for each processing node, we impose at most a 3-second delay. So for 1 node, we have to be below the first line. For 2 nodes, we have to remain below the second line, etc. And we're going to compare 3 variants of our technique. In the red variant here on the right, we're going to process tentative tuples as they arrive in upstream failure, but during reconciliation, we're going to completely suspend processing tentative tuples. And as you can see, if we suspend processing tuples during stabilization, we fail to meet our availability requirement. The maximum processing latency exceeds the 3-second bound. Yes?
This is because the actual work involved in doing the processing is great, because you're actually running, these things are CPU bound? Is that where this delay is coming from?
Yes, so this thing is CPU bound. So here the delay comes from the time it takes us to reconcile. So I was running here with about a 20-second failure. And once the 20-second failure heals, to reconcile and reprocess this 20-second worth of data, it takes us longer than 3 seconds. But what is interesting in this result is that even if we did meet our 3-second requirement for the first node, the maximum processing latency increases greatly for each node in the chain. And we completely fail to meet the availability requirement. The maximum processing latency is very high. So basically, we have to meet the availability requirement, we have to continue processing the new tuple both during upstream failure and during stabilization. But we can do this in one of 2 ways. And those are the results in blue and green. So the green one is the one in the middle. One way in which we can do this is that we're always going to process tentative tuples as they arrive. And this is the result in blue on the left-hand side. And as you can see, this gives us the best availability. This leads to the lowest maximum processing latency. The alternate technique is to always run on the verge of breaking the availability requirement. So every node in the chain is going to receive results, and it's going to always wait as much as possible before processing these results. So of course, the availability is a bit worse because now each node is going to add this almost 3-second delay onto the tuples that it processes. So this is worse, but this is still within our requirements. So we're willing to pay this price if we can gain in terms of consistency. So let's look at the number of tentative tuples that the application sees. So in this graph, on the x-axis, once again, we have the depth of the chain. On the y-axis this time, we have the number of tentative tuples measured at the output of the whole chain. So as you can see, for 1 node, indeed, delaying processing tentative tuples does lead to fewer tentative tuples on the output. However, what is interesting is that as we increase the depth of the chain, not only we do not gain in terms of consistency, but delaying can actually hurt our results. We actually produce more tentative tuples. And what is happening is the following. When the failure first occurs, each node in the sequence adds this 3-second delay to the inputs that it's processing. However, when the failure heals, the first node starts reconciling. As it does so, it does not delay any longer. It processes input tuples as they arrive. But the second node is still in failure mode. It's still just correcting its input streams. So now, because the input tuples arrive without any more delay, rather than delay by 6 seconds, the node has to reduce and delay by only 3 seconds. So basically, the nodes are catching up. And they're catching up while processing more tuples because we are now reconciling. So this is why we get more tentative tuples on the output. So overall, for long failures, processing new tuples without delay gives us the best availability and consistency. Yes?
This is interesting. This basically means if you have a feedback in your processing graph, it's going to be unstable. You're going to have unlimited number of tentative tuples.
So basically, in the current processing modes, we do not have cycles in the graph. The processing is an acyclic graph. So this is the processing model that we have. And it would be actually interesting to see how to reconcile if we had cycles.
Right, but presumably for short failures, you have exactly the opposite result. Right, if you get small time glitches in here, delaying allows you to not generate any tentative tuples at all. So if you
Correct.
have, if you have
So
a
we still-
2-second failure,
So we still always delay before going into any kind of inconsistency. But the idea is once we do process these tentative tuples, so once a failure is short, we always delay, and every node is going to delay. But when the failure is longer, then we start producing these tentative tuples. Then we can either continue to delay these tentative tuples always as much as possible, or start processing them without delay.
right, and the trade-offs, if I understand what you said, the trade-off winds up being that when the time to catch up gets so large that you can't catch up quickly and still have to generate the tentative tuples out at the end of the chain. That's what's going on?
Correct.
So if you had a 4-second outage, for instance, so it's long enough that you do have to generate some tentative tuples.
Correct.
But short enough that the catch-up work wouldn't be, would you expect the green and blue lines to be reversed?
Actually, not necessarily, because what will happen here is that still every node is delaying one after the other. And they're going to, so every node is delaying by this increasing additive delay. Once the first node reconciles, and as soon as it reconciles, it's going to send the data to the downstream node. So the downstream node now receives all this data quickly. So the only time in which you could still save something is if this reconciliation time for the downstream node is still extremely rapid.
Which for a small bit, but it probably is.
So you might have basically, so if you look kind of at a final result, there's only a very short window of time in which you might still gain.
Well, I mean, it's huge. This is going to depend entirely on the performance of the machines, the particular operators that you're doing, and the data rate.
Correct, but basically, so we can talk more about this offline, but basically what happens is that if the failure is so short that you just block without inconsistency, then it doesn't matter. So the failure has to be longer than this. Once we process data, when the first upstream node starts, so now every node is going to add this increasing delay. Once the node is going to now go back and reconcile the state, it's going to produce all the corrections in one burst, and only then the node is going to reconcile. And that reconciliation would really have to be much faster than the processing delay to really still gain something.
Which it may or may not be, depending on.
So basically, so I run different experiments, and that window ends up being quite small, in which case you might still gain. But we can talk a little bit more offline. I have a few more slides that kind of explain the details of what's happening here.
Okay.
But for longer failures especially, it's really not worth to delay the processing. And there's only a very kind of small window where it's still worth it to do this. Okay, but if you look in terms of other related work, so for stream processing engines, and especially for distributed stream processing engines, the previous techniques either did not address the problem of network failures or strictly favored consistency. And this is for other types of stream processing engines. So what you're actually proposing is more similar to other techniques for replication-based fault tolerance that have been used, for example, for databases or file systems. And in some of those techniques use what is called lazy replication with also tentative transactions, where the different replicas are allowed to continue processing the updates that they see, even if they cannot talk to each other. But they process these updates as tentative, and later asynchronously talk to each other to determine what the order of the update should be, and they reprocess these updates as committed. So what we have proposed is a very similar model, but we propose it in the area of those stream processing engines where the state is no longer persistent, like in a file system, but is this large, rapidly changing transient state. And our definition of availability is to make sure that the processing latency remains within these, within a specific bound. So this is what I wanted to say in terms of fault tolerance. So I don't know if I have a little bit of time left. We have. So I would like to spend maybe a little bit, about 10 minutes, talking about some work that I have done for load management. So this is a different topic. So we can now basically ignore all fault tolerance issues and only look at load management and what happens if we are varying the input load on the system. So the load management problem is the following. We have these operators that we're running at the different nodes. Each operator is like a continuous task. And this task imposes some load on the CPU network bandwidth resources at any specific node. So what we would like to do is, as the load varies, we would like to move these operators around, maybe not even to ensure optimal load distribution or optimal load balance, but at least to make sure that none of the nodes is getting overloaded such that the processing latency remains bounded. And this is actually a well-studied problem, and there are different algorithms that exist to address this issue. However, most of the techniques look at a collaborative environment where all the nodes are happy to collaborate with one another to ensure the well-being of the whole system. But many of our distributed systems are deployed nowadays in federated environments, for example, in a peer-to-peer network or in a grid computing network, where different autonomous participants own and administer different sets of nodes. So the problem that I'm going to address is how to enable this load management, how to make sure that no participant in such a system is overloaded, while assuming that all the participants are autonomous and therefore all selfish. So what characterizes federated systems is that participants do collaborate with one another, but they only do so if they can benefit from this collaboration, if they can gain from the collaboration. So if you would like now those participants to move and handle each other's load, what we need to do is first we need to give them incentives to do this. Participants will not handle load on behalf of other participants if they do not gain from doing that. Second, we want to provide a scheme that is simple and practical so people actually use it. Otherwise, if it's very complex, then the participants might not want to get involved and increase the complexity of their system. And finally, because many participants are actually real humans, so because there are really humans behind every one of those autonomous domains, then they will develop naturally different preferential relationships with one another. So what we would like to do is enable them to leverage these preferential relationships and customize their load management agreements with one another. So these are our 3 goals. And as you can see, this is a general problem. This is not just a problem that affects stream processing engines, but it can be applied to other types of federated systems and applications that run in such systems. So more specifically, our problem definition is the following. We assume that every participant has a cost function. This cost function will give, for each input load, it will give us a certain maximum processing cost. And we assume that this cost function is monotonically increasing and convex, which means that each participant owns a set of resources. If nothing is running at the participant, then it's very cheap to process any task. But if the participant is heavily loaded, then it's going to be very expensive to run any kind of computation at that participant. We also assume that each participant has a maximum desired load threshold. And our goal is to make sure that not necessarily the load is distributed optimally between the participants, but that all participants remain within their maximum predefined bound. And this is what we define as acceptable allocation, such that the load is distributed in a way where every participant is going to operate within this maximum bound. So actually, load management in these types of federated systems is a problem that have also been addressed in the past. Companies typically use a static assignment. Either everyone handles their own load, or a company might subcontract its load management to another company. In terms of mechanism design, people have proposed the use of a central optimizer, where all the participants reveal their cost to the central entity, which then computes the optimal load allocation and the compensating payments. The problem is that a static assignment is not very flexible, and a central optimizer is not really implementable. Who should be the central optimizer in practice? So at the other extreme, people have proposed schemes that use auctions and also computational economies to move this load around and perform this load allocation. So in these systems, every participant auctions off their resources or auctions off their tasks, or even continuously changes the price of its resources such that supply meets demand. And in these systems, we can get very good load distribution. The problem is that we have to pay a large overhead cost in running all these auctions, in continuously renegotiating prices. And also, all the participants are just supposed to openly collaborate with all those others. It is very difficult to have preferential agreements. So what we propose is to use something in between. We propose that participants negotiate contracts offline and then use these contracts to perform their load movement at runtime. So our scheme is therefore going to be much simpler and will have a lower overhead than these computational economies, yet it still gives us good load distribution, and because the contracts are negotiated offline, they can be highly customized with various service level agreements. So overall, our approach is the following. We assume that offline, participants talk to each other and negotiate these contracts. And a contract can have various clauses. But most importantly, what we require is that the participants negotiate a fixed price for each unit of load. At runtime, a participant will only move load to its partner, and the partners will pay each other this pre-negotiated price. So here is an example. Let's say we have two participants. Everyone has its own convex cost function, and they negotiate a contract with a fixed price. This price will correspond to the gradient of the cost function for some load level. And this load level can be different for each one of the participants, but most importantly, it has to be below their maximum predefined load threshold, such that if a participant is overloaded, the unit marginal cost for processing a task will be greater than the contract price. And if a participant is slightly loaded, then the unit marginal cost for processing that same task will be less than the contract price, and it will be beneficial for both participants to perform the load movement. So let me show you a concrete example of how this scheme works. So I'm going to run 3 Borealis nodes. These nodes are going to have a contract with one another. The load is going to be this network monitoring query that I have shown at the beginning of the talk. So what is interesting in this experiment is that it's going to be a simple example, but a real example. The query that we are running is actually going to tell us if there are any suspicious IP addresses. And the input load that we're going to use comes from real traces of connection summaries gathered at an ISP in Utah and also at a router at MIT. So what you can see here is that in the bottom window, we have the load at each one of the processing nodes. So we have 3 nodes, and the load is not uniformly distributed, but we do not have any reallocations because our scheme does not try to ensure any kind of optimal load distribution. In the top window, in the white window, you can see the output that the client sees. So every time there's a suspicious IP, the client can see the IP address, and this is what appears in black. And you're going to do this even though we're going to move the load between the nodes. And as you can see, the load naturally increases for one of the nodes because the load naturally increases on one of the traces that the node is processing. And eventually, the load exceeded the maximum predefined capacity of the node. And the node had to move the load, so it used its contract with the green node to move all its excess load in a single load movement. But the load continues to increase at the red node. However, for the green node, which has just received load, it is no longer cost-effective to accept any more load. So the red node has to use its contract with the second partner, the blue node, to move the remaining of its excess load. And at this point, we have achieved acceptable allocation where all the nodes operate within their capacity, so no other load movements will occur. So there are several properties that our scheme has. First, we can have a fast convergence. As you can see, because we always compare the unit marginal cost to this fixed price, in the best case, we can move all the excess load within one load movement. We also have a low communication overhead because a node can only talk to one of its partners at a time. We don't need to broadcast and have auctions across all the partners. And also different participants, by moving the load, they basically have 3 strategies at runtime. They can either accept load at the pre-negotiated price, offer load at the pre-negotiated price, or do neither. And by accepting load when the unit marginal cost is less than the price and offering load when the unit marginal cost is greater than the price, the different participants always improve their utility. So they have an incentive to participate. And finally, because the contracts are negotiated offline, they can be customized with various service level agreements. So of course, if all partners have a contract with one another, we're going to have acceptable allocation. But in some cases, we can have, for example, a network where we can have, for example, 3 nodes in a chain having the same contract. If one node is heavily loaded, the other one is lightly loaded. If the contracts have the same price, the node in the middle of the network has no incentive to forward load from one partner to another. So to create this incentive, we actually have to allow for some price variation. But if we allow the price to vary within the complete possible range, then we go back to auctions and open markets. So how small can we make the price range, yet guarantee that we get to acceptable allocation? And how many contracts do nodes need to have for us to get to this type of allocation? So without going into the details, for a uniform network with uniform nodes and contracts, the minimal price range has to be proportional to the diameter of the network of contracts, which is how far a task might have to go to get into acceptable allocation. And also it has to be proportional to the unit marginal cost variation for one task, because each node in the sequence has to be able to make a profit by forwarding the load from an overloaded to a more lightly loaded partner. In terms of the number of contracts, we look at this using simulations. So in this simulation, we run a network of 1,000 nodes to see if the system is actually going to scale or if we need to have a great number of contracts per node. And we're going to establish contracts randomly between nodes. And what is interesting here is that using this uniform bounded contract with as few as 7 contracts per node, we do get into acceptable allocation, even if we have started with about 20% of the tasks needing to be reallocated. So of course, in this experiment, the system as a whole is not overloaded. But what is also interesting is that even if the prices are fixed or the prices are heterogeneous, so the different nodes have contracts at different load levels, we do not quite get to acceptable allocation, both with about 8 or 9 contracts per node. We have reallocated all the tasks except about 0.2% of them. So few contracts per node suffice to get to acceptable allocation, and even if the contracts are fixed price contracts or heterogeneous contracts, we do get to good load distribution. So in summary, I have presented Borealis, which is one of the first distributed stream processing engines. And I have shown you 2 schemes. One scheme enables us to provide fault tolerance. So we guarantee that that every node processes the data that it can process within this maximum processing latency D. But at the same time, we ensure eventual consistency, and we allow applications this flexible trade-off between availability and consistency. For load management, I have briefly sketched the scheme that we propose that enables participants in a federated system to handle their load collaboratively. But in contrast to previous schemes, our scheme is much simpler and much lighter than any of those computational economies, yet it still leads to good load distribution. So before working on these distributed stream processing engines, I have worked on various other problems. So for example, I have done some studies of wireless LAN utilization and mobility of users in a wireless network. I have developed a peer-to-peer based resource discovery system that is now publicly available. With another student, we have developed a tool called Infranet that enables a user to browse the web even in the presence of sensor and without appearing like they're doing anything that the sensor might not want them to do. And also before joining MIT, I have done some work on software reengineering. But what is interesting is what should we do in the future? And what is fun with the stream processing area is that even though we have developed tools, we have proposed different algorithms, there's a lot of work that still remains for us to do. For example, we're currently processing using these relational tuples. But could we extend these systems to also enable someone to process a stream of raw text information? How about a video stream? Can you make it easy to write these applications that incorporate all these different data types? Or we only have currently limited support for someone to query current data and historical data. So could we expand this support? And rather than simply storing data in terms of just the raw tuples or sample of the tuples, could we do some stream mining and develop the models of the environments that we monitor, detect the various patterns that occur on the stream, such that someone can match the current data with some historical patterns that have occurred? But even outside of the stream processing, I think one interesting point with the current distributed systems is specifically that they are being deployed in these federated environments where we can no longer assume that either nodes collaborate or are malicious nodes, but that some nodes are selfish. They will participate only if they can gain from this participation. So how could we leverage this or incorporate this notion into the various systems that we build? So this is another aspect that I'm interested in exploring. Thank you.
Thank you very much. Any questions?
I have a question.
Yes.
So the Borealis nodes, do they have to buffer data for as long as failures can occur for?
So actually, in this talk, I have assumed that we do buffer everything. In practice, what we would like to do is, well, we will have to do for especially long failures, even if we do write some of the buffer to disk, we might want to bound how much data we're going to buffer. But there are two, basically, buffering all the data enables us to provide two guarantees. One, by reprocessing all the data, we're sure that all the nodes will go back in a consistent state. And second, we go back and correct all the output results that we have produced. So if we truncate these buffers, we might not be able to provide both guarantees. What is interesting is that most operators are what we call convergent capable. They only operate on a bounded amount of state. So basically, by truncating the input buffers, we might not be able to go back and reprocess everything, but we can, for example, rebuild the most recent consistent state if we buffer sufficiently many tuples. So the approach that is interesting is to enable applications to tell us, for example, okay, I know you might not be able to correct all the outputs that I will be seeing if the failure is very long. So I would like only to always have the corrections to the most recent 1 hour or to the most recent 10 seconds worth of data. And by doing so, we can basically truncate the buffers to only rebuild the consistent state and correct the most recent output tuples.